Hello all, hope this works well. If the stream does get a bit laggy, this is also recorded for later, so you can have a look at it then if need be. So we're looking at graphs of factorized cubic functions. Okay, so in exercise 6e, we already looked at graphing functions that look like this. Okay, so a x minus h all cubed plus k, where we have a is our dilation, h is our horizontal translation, and k is our vertical translation. And so we've done that. What we're going to look at now, though, is a more general form. Okay, the more general polynomial form, ax cubed plus bx squared plus cx plus d. Okay, the standard form, or general form, polynomial. To do this, we need to recognize that there's going to be up to 3 or 4 variations of this graph. Okay, unlike quadratics, square roots, hyperbolus truncus, where it's all very similar, cubics we start to get variations. Okay, with all of these variations though, we work by finding the x-intercepts and the y-intercept. Okay, we rely on that, we trust on that, we use them, and then we interpolate in between. Okay, so we've already looked at the basic form, okay, which has a point of inflection that we translate horizontally and vertically dilate as well, okay, which was this one up here. From there we can, okay, as we start to change the A, B, C, and D values, we start to get the graphs that look like over here on the right hand side. We have a Y-intercept cubic, okay, and when we talk about intercept, I'm talking about x-intercepts, because all cubics will have a y-intercept somewhere. They will all have a y-intercept, but we talk about the different variations in terms of their x-intercepts and how many they have. Okay, so we have a Y-intercept, which looks like this one. Okay, comes down, goes back away, goes back down through. The other version of it, and I'll draw it in green, could also be like that, okay, and has one intercept right there. We have this turning point over here that doesn't touch the axis. Okay. We then have the 2-intercept one, which is a more special version because it has a repeated factor where one of the intercepts is a turning point. Okay, it comes up, has a turning point at the intercept, and then goes back through at its second. Okay, its second intercept. So if you looked at a factorized form of this, it might be, well, this turning point's on 0. Okay, so it would be x, x, and then x minus 1. Okay, that's what this one would look like is factorized. But if we had the turning point elsewhere at some point A, we would have x minus a, x minus a. So we have a repeated, and then x minus the other intercept, which is over here. We have this repeated factor. Okay, whenever we factorize and we get 2 factors that are the same, that means it's going to be a 2-intercept cubic where one of the intercepts is a turning point. And then lastly, okay, I don't actually think it's any harder than the 2-intercept. Most times people miss the 2-intercept version. Lastly, we have the 3-intercept where when we factorize, we get x minus a, x actually, and this is different a's, b's, and c's and d's from the polynomial form, x minus b, x minus c. When we get 3 factors, that means we are going to have 3 intercepts. Okay, and they'll be at a, b, and c. So they are the 3 different types, 3 new types of cubics, the 4th type being the basic one, which we have translations. Okay, so let's have a go at graphing some of these. Sketch the graph of y equals x minus 1, x plus 2, x plus 1 by first plotting the intercepts. And it says no need for turning points because they actually find where the turning points are. Unlike quadratics, the turning points in cubics are not halfway between intercepts. Okay, they can be skewed. And if we go back, you'll see this one. It's hard to see, but that is not halfway between 0 and 1. Okay, that turning point. Same here. Okay, this turning point okay, isn't halfway between -1 and 2. That would be somewhere over there. Okay, so turning points aren't halfway between intercepts and cubics. When we do a topic called calculus, we'll show you how to be able to find where these turning points exist, but for now, we just go with, we don't have to plot them, which is something nice for cubics. Okay, so back to our sketch x minus 1, x plus 2, x plus 1. Okay, so we're going to use our null factor law. Okay, where x minus 1 equals 0, or x plus 2 equals 0, or x plus 1 equals 0. Okay, therefore we get x equals 0, x equals -2, or x equals -1. Oh, why did I do that? That's x equals 1 over there, back in the first one. X equals 1, x equals -2, x equals -1. Okay, so they're going to be, we've got 3 different intercepts, so we're going to have 3 intercepts. X equals -1, x equals +1, and x equals -2. Okay, so I'm going to label those quickly. -2, 0, -1, 0, and we get 1, 0. Okay, so from here, we could have 2 different types. I'm going to do little sketches up here, okay, just to show the 2 main types we could have. So we've got intercept, 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 intercept. So we could have one that comes up, goes down, and goes back up through, something like that. Or we could have it the other way around. It starts by coming down, up, back down through, and goes like that. Okay. That could be the 2 versions that we could have. Now, one way to know between the 2 different versions is finding the y-axis intercept. If we find the y-axis intercept, we can then have a good idea which way this is going through. So let's find our y-int by letting x equals 0. It follows on, okay, that y is equal to 0 minus 1, 0 plus 2, 0 plus 1 is going to equal to -1 times by 2 is -2 times by 1 is still -2. Okay, so we now have our y-intercept at -2, which is down here. 0, -2. Okay, so now we can start connecting the dots. We can start connecting the dots. Okay, so again, this might not be the turning point here. Okay, it's actually highly unlikely this will be the turning point, even though it's halfway between these 2 intercepts. So I'm going to draw coming down, something like that. Okay, going up. Okay, that's the only way I can connect those, and that means if this is going up and I have to go through this point, that means I need to curve like that, and then I'm going to keep going down. Something like this. Okay, so that's one way we can find out the orientation. Okay, there's 2 other ways we can find out the orientation. If it's this sort of starting low, curving, and then continuing up, okay, general trend of that graph is going up, the general trend of that graph is going down, what we could say a positive gradient, the general trend of this is a negative gradient. The other way we can know is by looking at the x cubed term. Okay, so for a x cubed, this will be when a is greater than 0. Okay, so we call this a positive cubic, okay, because it's going up, or the a in front of our x cubed term is positive. And then in this one, this would be for when a is less than 0. It's trending downwards. Okay? And I would know, even before finding the y-intercept, if I looked at this, x times x times x, they're all positive. They'll multiply to give me a +1 for my a value. So it's going to be a positive trend graph, which we got. Happy days. So that is that. And Jamal's just given me a comment saying that he can't see any of the stuff I'm writing. That is really annoying. Let's see if I can fix that. Okay. That. Okay. That's now appeared on my screen. I wonder if Jamal is still with us. That's a waste so far. Okay. You see now. Lovely. Okay, you can see. Now let's do a test to see if it keeps copying what I'm writing. This whole new streaming stuff is new. Okay. Let's see if it recognized that. I did some scribbling at the bottom. That looks good. That's appearing on my screen as being transmitted. Well, that means it's also not recorded. That in the initial video. Okay. We're going to have to go back and start this stuff again. So let me fix this quickly, guys. Let's discard the ink. And I will start from the start so you have a better idea and the recording will work. No, that's the wrong one. I want that one. Okay. Yeah, can you guys see that red squiggle up the top right hand corner? There's a bit of latency now. Yeah, lovely. Okay. Ooh, that's not the button I wanted. Okay, gonna stop that recording, start a new recording. Jamal sees the squiggle. Lovely. Jamal, have you subscribed to the channel as well? I hope you have. Okay, rightio. Let's start that again. For the recording, sorry if that seems like a very weird start. It turns out I got 10 minutes into the video and people couldn't see what I was writing. So I'm having to start again. Rightio. So this video we are graphing factorized cubic functions. Okay, so we've already looked at the most general form, ax minus h or q plus k. Okay, which has a standard dilation, horizontal translation, and vertical translation, and it looks like this. It has this key point, the point of inflection, and we move that left and right, up and down, and we dilate by stretching the graph. Okay. For the new form, we're going to graph the polynomial version, okay, the full ax cubed plus bx squared plus cx plus d. Now, the way we graph this is by factorizing it, so finding all of its x-intercepts and also finding its y-intercept. And when we do that, depending on how many x-intercepts there are, it's how we define these three different types of graph, is by how many x-intercepts there are. We can have either this first form, okay, which is a 1-intercept, one x-intercept right there. So it can come down, has a bit of a turning point here, goes back up, has a y-intercept, and then down through the one x-intercept. We can have another version of it, which could be coming up the other way, down, and then up that way. Okay, still only has one x-intercept. The second type is a graph that has two y-intercepts, x-intercepts, sorry, okay, where one of them is a turning point, okay, and then the other one is a proper through intercept. Okay, so when we have this two intercept version, it's also sometimes called a repeated factor. Okay, where this turning point here, if we factorize this, would look like x minus 1, and the turning point is whenever we have two factors that are repeated. So we might also have something that looks like x minus 2, x minus 2, x plus 1, whatever. When we factorize, it looks like that. Since we have two repeated intercepts, that means that repeated intercept is actually going to be a turning point. Okay, and then this third one will just be a normal intercept. Okay, and then the very last one is, that hasn't broken anything. The very last one is a 3 intercept. 1, 2, 3. Okay, now it can come up, go down through, we have a y-intercept there, but then we have our 3x intercept. And now what determines if it's going to be a 1 intercept, 2 intercept, or a 3 intercept are the terms a, b, c, and d. Okay, you can't really tell when you're looking at it in polynomial form, where it's in this full expanded form. You can't tell just by looking at the numbers what it's going to be, if it's going to be a 1, 2, or 3. You have to factorize it first and see how many factors you get. That will then tell you if it's a 1, 2, or 3 intercept cubic function. So there is that. The other way that we could have this one, again, is it could be flipped upside down, as if we had a negative. If you had a negative a, it would flip it upside down like that. So let's have a quick go at graphing one of these. And the nice thing is, this first example, we're starting already in factorized form. It's in factorized form, and we have 1, 2, 3 factors, and they are all different. Therefore, it means we're going to have a 3 intercept cubic. Okay, and remember, when we talk about intercept, I'm talking about the x-intercepts. So how do we find those? We use the null factor law. Okay. Null factor law. So we get x minus 1 equals 0, or x plus 2 equals 0, or x plus 1 equals 0. I just want to make sure that's still appearing. Yes, it is. Okay, so from that, therefore we get x equals 1, or x equals negative 2, or x equals negative 1. So we can plot those in. I'm going to just mark these with green, these intercepts. So we get the first one at 1, 0. That one there is at negative 1, 0. And our last one was at negative 2, 0. Okay, so we have our 3 intercepts. Now I'm going to do a quick little sketch up here. We can have a think of, there's going to be two different ways this could appear. It could be a positive or negative cubic, and you'll see in a second what I mean by that. Okay, one of them, okay, we can start with a positive gradient, come up, flip around, go back up that way, and end with a positive gradient. We start with a positive, we end with a positive gradient. Okay, we could have that way, or we could have it the other way. Start with a negative gradient, come down, turn, back around, and out. Okay, so started with a negative gradient, ended with a negative gradient. Now, which one is this going to be? Well, the quickest way and useful, because we need to graph it anyway, is find our y-intercept. Okay, so let's find our y-int. So let x equals 0, so we get y is equal to x plus 0 plus 2 and 0 plus 1. And that's going to give us -2. So we can plot that down here. Okay. So now that we have that, the only way that we can connect 1, 2, 3 dots is by coming down through that one, up through that one, and then keep going. Okay. So if this keeps going up and up, that means we have this first case. This is going to be a positive gradient, and as we go through this dot, the only way to get through our original first dot is we have to turn around and come back down. Okay. So we have that. From here, okay, there's a couple things I want to point out. One, this turning point here and this turning point here, okay, we don't have to find them. It says no need for it, okay. And two, unlike quadratics, they aren't always halfway between intercepts. If we go back to the previous slide, we can see this turning point here, okay, is definitely not halfway between -1 and 2. Okay, that should be over here. Okay, and same on this one, it's skewed off a little bit to the left. Same over here, that's skewed off. Okay, all the turning points aren't actually halfway between the intercepts. Unlike quadratics, that doesn't occur. There isn't a way to find the location of the turning point until I teach you how to do a topic called calculus. You could do trial and error and find where the number gets it's highest in this zone between -2 and -1. You could try there, try there, try there, and get a rough estimate where it is, but there's a more exact way using a topic called differentiation and calculus, and we could find the exact coordinates. But for now, we don't have to actually worry about that. So there was a sketch. There is two other ways though to know if it's going to be a positive cubic, okay, if it's going to look like this, or if it's going to be a negative cubic, okay, before finding the Y-intercept. The first and easiest way is looking at your cubed term. Okay, so every polynomial we have our cubed term. Okay, if a is greater than 0, it's going to be positive. Okay. If a is less than 0, it's going to be a negative graph. Okay. If a is positive, we can think the graph's overall going up. If a is negative, we can think overall the graph is going down. So that is really simple, and I could know that straight away looking at my x terms. If I did x times x times x, well, that's going to give me x cubed, which has a positive 1 as my a. So I knew straight away looking at this in factorized form, I knew it was going to be positive, so I didn't even need to find that to get a sense of the graph. So that's one way. There is a third way. It's more convoluted, takes a few more steps, uses a little bit of trial and error, okay, but it allows us to create a sign diagram. Okay, and sign diagrams are actually really useful, and you could think of them as a simplified inequality almost. We could use these to help us solve inequalities. When is y less than 0? When is y greater than 0? It's sort of a simplified, flattened out version. And it's saying the whole point of this is we have x going across horizontally, and then our vertical is our y. Is it positive or is it negative? It doesn't care if it's really positive or really negative, like is it +5 or +2 or +1? Okay, we're not sketching like this at its different points. We just care, is it positive? Okay, or is it negative? And when does that always change? That changes at the intercepts, okay? So this is an example where we have 3 intercepts at A, B, and Y, okay, or alpha, beta, and gamma, technically is what those symbols are. And we can see we have a negative sign in front, so that means it is going to be a negative ax cubed, so we know it's going to be going down, which it's drawn as here. Okay, so we can look at this, go, okay, it's going to be negative, so that means to the furthest left of the first intercept, my graph is going to be coming down. We know it's going to look something like this. I have my 3 intercepts. Okay, so it's going to start in the positive y zone. We're starting in the positive y zone. We get in the negative y zone, which is this. Okay. We get back in the positive y zone, which is this. And then we finish off with back in the negative y zone. So a sign diagram shows, are we in positive y or are we in negative y? Or are we above the x-axis or are we below the x-axis? Drawing these diagrams without showing you how to do it can be a little tricky, so I think it's easiest if we just jump straight to an example and show you how to do this. Okay, so find the factors of y equals x cubed plus 2x squared minus 5x minus 6. Hint, use the factor theorem and long division. So let's try the factor theorem. So we need to use a factor of -6. Okay, so I'm going to try, let's try 1 straight away. Okay, so y of 1 is equal to 1 cubed plus 2 by 1 squared minus 5 by 1 minus 6 is equal to 1 plus 2 plus minus 5 minus 6. That's no good. No good, so let's try y of -1 plus 2 by -1 squared minus 5 by -1 minus 6 is equal to -1 plus 2 plus 5 minus 6 is equal to 0. That did not equal to 0 up here. This equals to 0. Happy days. We have found a factor theorem. Or we found a solution. Okay, so we can say x equals -1 is a solution. Therefore, x plus 1 equals to 0. Or x plus 1, sorry, is a factor. So now that we have a factor, we can do the long division. Okay, you could keep using the factor theorem. You could keep trying different numbers. You could try -2, -3, 3, +2, 6, -6. You could keep trying them to try and find the other factors, or you could go straight to long division, or you could use the factor theorem. I'm going to use the long division because I always think it's something that everyone needs to practice more of. I'm not going to talk while I go through this. It will just be quicker. Okay, so that all worked out. We got no remainders, so we ended up with, I'm going to have to use some space over here. Actually, I'll go up here. We've ended up with x plus 1. I haven't done that far enough across. X plus 1, x squared plus x minus 6. Okay, so there was our solution to long division, so I can now further factorize that using inspection. I'm going to try and factorize the quadratic. So the -6 gives me +1, so that'll be +3 minus 2. 3 times -2 is -6, 3 minus 2 is +1. Okay. So I've factorized it. My function is now y equals x plus 1, x plus 3, x minus 2. Okay, so what are my intercepts? Well, we could use the Null Factor Law, but to shorten that up, we get x equals -1, x equals -3, x equals 2. Okay, so there are intercepts. So to now create a sign diagram, I'm going to put them on my sign diagram. Just mark intercepts. So you could put some values, a scale if you wanted to, if that helps. So I'm going to call that 0, 1, 2, 3. Okay, and now I'm going to mark them on. So x equals -3 there, and I just put a big through line, big vertical line through wherever they occur. Okay, because that's where my graph is going to cross the x-intercept. Okay. And now the second stage, okay, is finding what are my lines that I'm going to use to connect them. When is the graph positive? When is the graph negative? Okay, we could use our trick. Okay, sorry, I should say not when the graph is positive or negative, when the y value is positive or negative. Okay, we could use our trick of looking at a x cubed term, okay, and is it positive or negative? But the purpose of using these sign diagrams is let's do a little bit of substitution. Substituting a point in between each of the zones, okay, and find out what the value is. Is it going to be positive or negative? Okay, so let's go y of 0. Let's start with that first up. That's really easy because we're going to put 0 plus 0 minus 0 minus 6. So it's just going to equal -6. So at 0, our y value is equal to -6. And the important part of that is the negative. Doesn't matter what that it's 6. It's just that it's negative. Okay. So our y, is it positive or is it negative? At 0, it is negative. Okay, it's down here. So I can now draw this as in that whole zone, my y values must be negative. They can't get back to positive without crossing through the x-axis, which only occurs at the intercepts. So that's that. From here, you can make a reasonable guess that that's going to be across there, that's going to be across there, that's going to be across there. But let's double check. Let's go y of halfway between these two zones, let's go -2. So we get -2 cubed plus 2, -2 squared minus 5 by -2 minus 6 is equal to -8 plus 4 plus 10 minus 6 is equal to 14 minus I've done something wrong there. Yes, -2 squared is 4 times by the 2 is 8. Yeah, there we go. That's better. 18 minus 14 is equal to +4. Okay, and just like before, we don't really care about the number. We care is it positive or negative. We got a +4. Okay, so in between -3 and -1, our graph is going to be positive. Okay, and then it crosses. Well, from then on, our graph is going to be negative, and off this end, it's going to be positive. Okay, so that is a sign diagram. It's telling us are our y values positive or negative and what zones they're occurring. Then once you have that, you could then use them to draw your graph. Okay, so continue the sign diagrams. Using the sign diagram, sketch the cubic. Okay, so let's go back. Our intercepts are at -3, -1, and +2. Okay. We then knew it was positive greater than 2. So it needs to be going up like that. We know it was positive between -3 and -1, so it must be doing something like that. Less than -3 down this way, it was negative. So my graph is going to go like that. And the last thing would be drawing in this final connection, but I'm not going to draw it in until I know the very last thing is my y-intercept. Let's find my y-int, and I actually already found it because I did y equals 0 back here. Y is 0 equaled -6. Okay, so 1, 2, 3, 4, 5, 6, way down here. Okay, so this actually needs to be a lot steeper. Okay, so that is very roughly, there's our intercept. I'll put the y-intercept in different color. Okay, and same thing, we can't assume that that's where our turning point is. That was 0, -6, that was -1, 0, -3, 0. Okay, so sketching cubics can be a little messy, and doing on this tablet I can't erase at the moment, so that's a bit of a pain. But getting the idea how we could use our sign diagram. Okay. It's much more intuitive using just recognizing which way it's going to be rolling through. Okay, using this idea of what's our a, is that my a greater than 0, whereas my a less than 0. It's much more intuitive once you recognize and get used to the pattern and shape of what cubics are going to look like. But sign diagrams, you do need to know how to use them because they do get used in applied cubic work. And 2, they are really handy to avoid yourself getting into trouble when you're dealing with repeated roots. Okay, because a sign diagram for a repeated root would look something like this. The graph would actually be negative, come up, it touches the x-intercept, comes back down, stays negative, and then goes through. Okay. If you just assume using this whole idea of the a with a repeated root one, then you might make mistakes. Okay, right, and here's a great example. If a factor is repeated, e.g. y equals x minus 1 all squared, x plus 3, then there are only 2 intercepts, and the repeated factor is also a turning point. Sketch y equals x squared, bracket x minus 1 by first making a sign diagram. Okay, so what are our intercepts? Well, this is really this x squared in here. I could rewrite this as x minus 0 all squared, x minus 1. Okay, so our first intercept is at x equals 0, and the second one is at x equals 1. So go to our sign diagram and put those in. All that. I can't undo that. It's annoying. We'll call that 0. Actually, see if I can erase. Yep. Okay. Now is my pen going to have it whack out? Yes, it is. There we go. Okay, that's why I don't like erasing, because my tablet has a whack out. Okay, 0, 1, 2, -1, -2. Right, intercepts at x equals 0, and that's this one here. Okay, times 2. It's a repeated root. Okay, so that is going to be a turning point there as well. And then x equals 1. So I can draw a line through x equals 1, and I'm actually going to draw a dot at the repeated root because it doesn't go through, it just touches. Now, is it positive? Is it negative which side of my sign diagram and am I going to be for my y values. Well, let's substitute in a point. Let x equal somewhere to the left. Let's go -1. Y is going to be equal to -1 squared. -1 minus 1 is equal to -1 squared is 1 times by -2 is going to be -2. Okay, so importantly, it is negative. So I can now draw my sign diagram. Over this side, it is negative. It gets to 0. It's going to come up and touch. Okay, it's touching. It's going to come back down because it's a repeated root, go across, go through the next intercept. And that's what my sign diagram is going to look like. Okay, so now we can sketch it. So my repeated root is at 0. I have an intercept at 1. So my graph is going to come up, touch, come down, and go back up through. Okay. So the shape stays the same. It just happens to be that one of the intercepts is a repeated root. And that's how we sketch that. All right, now the last one is if we have a 1 intercept. So we've sort of worked backwards here. We started with 3 intercepts, then 2 intercepts. So 2 intercepts, okay, is the repeated one. And now we're looking at 1. Now 1 is if the factor is repeated 3 times, or we get x minus 1 and then this quadratic, okay, quadratic can't be factorized. Okay, we can't factorize this, so that means it just has 1 root. Okay, now I'm not going to do the cas part of this. I'll leave you to do the cas part. The function for that is max or min. Okay, you want to use those two in your cas to find what the max or min is. But we have a negative x minus 1 x squared plus 5x plus 7. Okay, so the factor, the intercept, is at x equals 1. So that's there. Okay, and it's a negative. Okay, so if we remember, a negative cubic comes down, up, and goes down. Gradient starts negative and finishes negative. Okay, and if that's my point, well, I must be going through it like that. It's going to come up and do something like that. Okay, now the actual locations of that bit and that bit you can find using your cas, but we know that that is going to be 1, 0. And the other point that we want is our y-intercept. So let x equals 0. We get y is equal to -1, 0 plus 7 is equal to 7. So that point there is 0, 7. So there is a 1 intercept graph, 1 x-intercept graph. That's it for this exercise. I will hang around if you want to type in any comments on YouTube quickly. There'll be a little bit delay before I appear them because of the stream delay, but happy if you want to ask any at the moment. Well, if you do think of any, you can ask me on Edmodo. That's completely fine. Or put them in the chat to this video. That's fine as well. Otherwise, I will finish up there.